Hello AP Chemistry and welcome to a representation of orbitals. So these are the different ways we can look at orbitals and just some information you should know about orbitals. So if we look here, right, this is kind of what we looked at in the previous lecture, where this is an electron density diagram. Where we see here, right, where we have more dots, right, that means a higher probability of finding an electron, right? Where we have fewer dots, there's a lesser probability. And this is an electron density diagram for an s orbital, right? Where s orbitals are spherical in shape, and so this is the area where we might find it. This, right, would represent our nucleus, right? The center of all my axes, the origin, would represent my nucleus, okay? Here we have some contour diagrams, where they sort of represent the hard edge of my orbital, right? Wherein this would represent the outer edge of my s orbital, right? And the electron can be anywhere inside of there, right? Likewise, anywhere inside of here or anywhere inside of here. Which again, going back to what we talked about, here my shell number indicates distance from the nucleus, right? And the larger my shell number, the further I am from the nucleus, which in a couple of sections we're going to talk about why 1s electrons are so strongly attracted to the nucleus, and that's because of their proximity, right? These are going to be closer than these, which will still be closer than these, okay? And we mean closer on average, right? Because we don't really know for sure, right? But closer on average. All right. Another way to look at s orbitals, all right? Here, if we look, and let's say you're like, what? What is this? Well, trust me, it's not that difficult. You just have to pay attention to our axes. So, probability, right? Which means that the higher up we are, the higher the probability. Here, this is distance from the nucleus. Okay, this is referred to as the angstrom. Angstrom, which is a measurement of 10 to the negative 10th meters. Okay, so kind of like how mega means 10 to the 6th, right? Micro means 10 to the negative 6th. Angstrom, now angstrom doesn't get attached to meter, right? So it's not like an SI prefix, but angstrom just means 10 to the negative 10 meters. Okay, so anyway, so what this says that 1s orbital, right, on average, those electrons happen to be approximately 1 angstrom from the nucleus. That is the average distance, or the most likely distance, to find an electron. We can find an electron all the way up to the nucleus, and we can find them out almost to just past 3 angstroms, right? And this is the most likely place to find a 1s electron, right? If we move over here to a 2s electron, we'll see that, again, we can find it over here, and we can find it a little bit further away on average. But what do we notice here? Right, a node, where a node is a place of 0 probability. What do we notice about my node relative to over here? Right, okay, we notice that my node happens to occur where my 1s orbital has the highest probability, right? So going back to the concept of electrons having wave-like behavior, right? If this is where we have a peak of 1, right, then the other one can't have a peak there, right? Does that make sense, right? If my 1s peaks at 1 angstrom, right, then my 2s cannot peak at 1 angstrom. It'll have a peak before it and a peak after it, okay? And so we'll have one node. By the time we get out to 3s, okay, we'll see that the average, or the most probable distance, right, starts to be about 7 angstroms from the nucleus. And we'll see that, again, we have a node at 1, which represents where this peak is, and we have a node at 3 and change for where this peak is. Yes? Does that make sense? And if we had 4s, it would have nodes at 1, almost 4, and around 7. Yes? Does that make sense? Okay. Which again, going back to the fact that 1s electrons are closest to the nucleus. Okay. Next up, p orbitals. We describe this as being a two-lobed shape, okay, where this is one area of probability, another area of probability. And there are 3 of them, and they lie on the x, y, and z axes, right? So we have one p orbital here, one p orbital here, one p orbital here. And again, the orbital just represents a place where 2 electrons might be. Note that we're not saying that the electron's moving in a figure 8. That's not what we're saying, right? We're saying that the electron could be anywhere in this space, okay? Now, one other thing to point out. You'll see here, right, that there is not electron density here, okay? And that is why we say, right, and we'll talk more about it later, obviously, when we're going to talk about periodic trends, But here, p orbitals are not as close to the nucleus as s orbitals, right? And we would call that nuclear penetration, okay? In that s orbitals penetrate closer to the nucleus than p orbitals do, okay? S orbitals penetrate closer to the nucleus than p orbitals, okay? Which we can see here in our either of these diagrams, but the electron density one shows it really well. There's almost no density here, whereas when we go back here, that's where our region of highest density is, okay? Just one of those little tidbits to bear in mind. All right, d orbitals, the shape gets more complex in terms of where an electron might be. You don't actually need to know these designations, but you need to know, right, that it's a set of 5 and they get more complicated. F's get even more complicated still, so much so that your book doesn't even bother showing them. So, anyway, this is what our orbitals kind of look like. And again, remember that these are just where electrons might be. These aren't how an electron is moving or where it's moving, just where it might be. Okay, which means that all those little figures you see with the little swirling, electrons moving in like little orbits, that's not true, right? It's fun to look at, but not true. Okay, thanks for listening, be good, and stay tuned for the next one, where we'll talk about actually writing some electron configurations. Be good, bye.